All right, we are on 6-2, circle theorems. Circle theorems come from the information that we talked about last time with inscribed and central angles. Circle theorems are things that have been proven to be true all of the time, that's what makes them theorems. What they are, and I remember how people saw these things. They look at them and they think, oh my gosh, I don't know what's going on at all. So I will tell you, you do know what's going on. These are formulas. That's what they are. You use them the same way that you use formulas. So if you know a piece of information, you just plug that piece of information into these theorems, and then you have some missing information there. So they are just telling us relationships between angles inside of a circle, angles and arc measures inside of a circle, and we just use that relationship just like a formula. So that's my preface here. The first one that we're going to talk about is internally intersecting secants theorem. So really we just have two line segments, technically, intersecting inside of a circle, and I will note that it's not in the center, right? This is a different point somewhere else. And I will highlight these. I will try my best to highlight them so that they make sense. So the relationship is that the measure of angle DFE, which is this angle right here, measure of angle DFE, there we go, is half of the sum of the measure of arc BC plus the measure of arc DE. So BC and DE are these two arc measures. Oops, different colors. So what you do is you add the two arc measures. That's what we're doing here. We're adding the two arc measures, and then we're dividing by 2, and we get the measure of angle DFE. And you might also remember, something we'll review, but this angle and this angle are also the same. So it doesn't matter which one you're looking for, you can get this angle or this angle using this formula. We'll practice that. But again, this is a formula, so if you know this one or you know this one, you can plug those things in and do some math, and it will give you this. Or maybe you're looking for a different one and you have to solve for it. We'll do some examples later, but this is just a formula, specifically for when two secants are intersecting each other. Now we have externally intersecting secants, which means the lines are intersecting outside of the circle instead of inside. We're going to use this angle. So angle KEC is this angle inside of here. I will highlight it. Angle KEC. That one is equal to half of the big arc minus the small arc divided by 2 gives you the outside angle there, angle KEC. So it's blue now. That's how I've highlighted it. So half of the big minus the small equals the blue angle. This is also a formula that you can use in any sort of situation. Here's one that we like a lot. Parallel lines make congruent arcs. So if you have two lines that are parallel, so these two lines are parallel, meaning that they would never intersect because they have the same slope. Those two lines are parallel, then these two arcs are equal. That makes sense, right? Because if you're intersecting a circle with two parallel lines, their inside arcs should be equivalent. I'm trying to think if we have any different thing to say about this. No, not really. Those two things are the same. I will remind you that this might look more confusing, but remember that central angles are the same thing as their arc measures. So if we had something like this where central angles have the same arc out here, that means the central angles are also equivalent, right? Because central angles are the same thing as arc measure. So you might see that somewhere. That's all. Okay. Next we have tangent and radius theorem. So if you have a tangent line that intersects the circle at a single point, which is B, then those two things are perpendicular. So this symbol right here means perpendicular. That means that these angles are 90 degrees, both of them. Because you have a radius at point B and a tangent line at point B, that means they're 90 degrees. I will highlight this one. So this is line EUB, which is that piece, and this is radius BA, which is that piece. They're always 90 degrees perpendicular. Circumscribed angle theorem. So this is a combination of a couple of them. It makes a kite. This shape that it makes out here is called a kite. It also looks like a kite, which is helpful. So we have that just the measure of angle alpha. They're called alpha and beta here. Alpha and beta equals 180 degrees. The thing that I want you to notice here is that this kite, that's a four-sided shape, right? Even though it's like a weird four-sided shape and it's a kite, which is something that we haven't really messed with a lot. We have a kite, and two of the angles have to be 90 degrees because they're coming from two tangent lines intersecting radiuses, right? So the central angles, I'm just going to write this first. Four-sided shapes have an interior angle sum of 360 degrees. Interior angle sum of 360. Triangles have 180. Four-sided shapes have 360. So if we already have two 90 degrees accounted for, then the other two have to add to be 180, right? Because we have two 180s make 360. So that's how come angle beta and alpha here add to be 180. So they're just sort of opposites. I'm going to pull out a word that you maybe don't remember, but they're supplementary, right? They add to be 180. Okay, so those are our theorems. I will come back to this page in a second a lot. It'll maybe make you dizzy, I'm sorry. But we need those formulas in order to make some headway on these problems here. So this first one is asking for the measure of, let's look what we're looking for here, the measure of angle KC. We're looking for the arc measure of KC. And we have, that's 36.5 degrees. This angle out here is 47. So I will show you here, that picture looks very much like this picture, right? So we should be using this formula, just that the big arc minus the small arc divided by 2 equals the blue angle outside. So, and I highlighted them differently, which is not helpful of me, I'm sorry. So let's just call this angle X, because we don't know what it is, we're looking for it. If we do X minus 36.5, that's the big angle minus the small angle, divided by 2, or multiplied by 1/2, either of those, equals the green angle, which is 47 degrees. Now our job is to just solve for X. We've put everything that we know into the formula. Maybe I'll highlight here. So we have 47 degrees, 36, X. Okay. Now we just have to solve. So what I'm going to do first is multiply by 2 on both sides, because we have a divided by 2 or multiplied by 1/2. Those are the same things. I'm going to multiply by 2 on both sides. That gets rid of that, and we get 94 degrees on that side equals X minus 36.5. And then we can add, this is just algebra, add 36.5 on both sides. And we get, let me see if I can do this in my head, 90, 120, 130.5. I might be wrong, let me check. 130.5. Nope, that's it. So our arc measure that we were missing is 130.5. 130.5. And we just used the formula and did some algebra and figured out what was happening there. Number 2, we have two lines that are parallel, and I'll tell you how I know that. These symbols mean that they are parallel here. So we have two lines that are parallel, and there's only one theorem talking about parallel lines, and that's this one. So we have two lines that are parallel, and that just means that the two arcs that they make are equal. Arcs inside of them are equal. So that means that this arc, let me highlight them, this arc and this arc are the same, and this one is asking for the measure of arc NC, which is over here, arc NC. I know they're the same. I also know that there's an inscribed angle here that I'm coloring blue, an inscribed angle that's attached to that yellow arc, the other yellow arc. So inscribed angles have the relationship of being half what the arc is, right? So 40 degrees would be half of whatever this arc is. So 40 times 2 would get us 80 degrees. And since that one's 80, we also know this one's 80 because they're the same. So that's the answer for that one. They're both 80 degrees. And we found that out because of this inscribed angle of 40 degrees. Okay, number 3 here, we had this one is very interesting, right? But I will point out that the first thing I notice here is that this and this intersecting inside of a circle looks very much like the first picture we have. The first theorem, which is the internally intersecting secants theorem. So our formula is that if we add the two arcs and divide by 2, then it gets us the interior angle. So we're adding the two arcs, and we get this value here, and divide by 2, and then get that value. So I'm just sort of plugging stuff into my formula. 77 is the value we would get if we halved 92.8 plus, and I'm going to call this x because I don't know what it is yet, plus x. So now we just have a little bit of algebra to do. I'm going to multiply by 2 on both sides, so that goes away. And then I get 154? Yep, I was double checking. Equals 92.8 plus x, so I'll subtract 92.8, subtract 92.8, and we get 61.2 equals x. So that is the value of the green arc. So maybe I'll highlight it here. So that's the green arc. Hang on, I can highlight a lot more here. 92 and nope, that's green. X. So x is 61.2. I didn't even look at what we're looking for. This is saying we're looking for the measure of angle FGC. Sorry. That is, maybe I can get a different color here. That's this angle, FGC. And now we're going to ignore the two intersecting arcs because we know what x is now. We know x is 61.2. This is 61.2. And then we have an inscribed angle attached to that arc, which is half of what that arc measure is. So we can just divide by 2 to get the angle measure that we're being asked for, which is 30.6. We decided? Yes. 30.6. So if we do 61.2 divided by 2, that makes 30.6, which is the measure of that angle. Because of the inscribed angle. That's that. Let's talk about this one. This one's always fun. For some reason I forget how to do it every year, but I do remember this year. So we have a sort of a weird four-sided shape inside of a circle here. So what I want us to do is, and we're looking for the missing angles inside of the circle. So I want us to remember back to the triangle that we had inscribed into a circle from last lesson. And I want us to notice that we have an inscribed angle here attached to an arc. So the whole orange arc is attached to this 81 degrees angle. So I'm going to just really quickly, 81 times 2 gives us that arc measure, which is 162 for the orange, 162 degrees. The whole orange, right? Not just to this line, but the whole thing. And then there's like sort of a paired opposite angle, D, which is attached to this whole arc over here. Here's an inscribed angle, right? Attached to this whole arc. So we can actually figure out what the green angle is just by subtracting 162 from 360, because they're taking up the whole circle when they're paired like that, right? So if I have 360 minus 162, that gives me 198, I believe. 198. And so then I know that this is half of that. So 99 degrees? 90? 100, yes, 99. So the measure of angle D is 99 degrees because it's half of that arc measure. Now we're going to forget about all of these lines that we just did, and I will like physically erase them because they're worse when they're there. They don't help us with the second part. So there we go. I'm erasing them. Now we sort of have this opposite situation where we have a 102 angle attached to this arc measure. I'll draw that again. Inscribed angle attached to that big arc, which means that that's going to be twice as big, times 2, as 102, which is 204 for this orange. Let me get an orange marker. 204 degrees for that orange. So then we are doing the same thing here. The arc angle A is inscribed attached to the other half. Well, I say the other half, but I use that loosely, right? The other half of the circle. So I'm going to subtract 204 from 360 because 204 and whatever pair the green arc is takes up the whole circle. So we know that they must together equal 360 degrees. So that means that the blue measure is green, 156. I'm saying blue because I'm looking at my other paper and it's blue on there, which is a terrible idea for me. So I subtracted 204 from 360, got 156, so that's over here. And because that's inscribed, we can divide 156 by 2 to get the measure 78 degrees for the other one. So that one sort of we did in like halvesies, right? So 81 and angle D were two parts of the circle, and then A and 102 were the other side. Number 5, we have a picture that looks somewhat like this picture. And so we know that the two angles add to be 180 degrees. So we have 111 here and R here. So we know that 111 plus R have to equal 180 degrees. Equals 180. Which we just do a little bit of math, take away 111, and we get 69. 69 degrees for R, because we know that they have to be add to be 180. And then it asks, number 6 is using this picture looks like that. which just says that they're perpendicular, so the angles in between are 90 degrees. And conveniently, it's asking for an angle ABD, which is this angle, which I will already tell you by drawing it in as a square that is a 90-degree angle because they are perpendicular. That's just what the theorem says. So, easy peasy. So that's some of our circle theorems. I realize that they can get kind of complicated, or at least look complicated. So if you need help, let me know on the homework. One more thing to do, we're going to talk about inscribed shapes, and this is hopefully a topic that won't be too bad. So an inscribed shape, that is not how you spell inscribed, inscribed shape is one whose vertices are on the perimeter of a circle. So polygons inscribed in circles have special properties. So inscribed shapes just have all of their corners on the edges of a circle. They're just like inside of a circle. We're going to talk about this proof really quickly. So first of all, to prove something mathematically, we use what we already know to show that something new is true. So we're using sort of a couple of facts, and we'll talk about what facts we're using to sort of lead others and ourselves to the conclusion that something new is true. In this proof, we're going to use our understanding of the sum of the interior angles of a triangle and the central and inscribed angle rules we discovered in the last lesson. So those are the things that we're going to be using. Interior angle sum of a triangle, which is 180 degrees, and the central and inscribed angle rules we learned. Those are the couple of facts that we're going to use. And we are going to lead ourselves to the conclusion that a triangle that's laid out like this, where this is the diameter, if that's a diameter and you make a triangle using that diameter, then this angle is always 90 degrees. That's what we're leading ourselves to that conclusion here. But we don't know that yet, so but we're gonna get there, right? So what is our given information? So given means what facts are we starting with? Different than what facts are we using to prove. This is the stuff that I just mentioned over here. RQ goes through the center of the circle. RQ and S are located on the circle P and form a triangle RQS. So RQ is a diameter that goes through the center of the circle. What does that mean? So since RQ is a diameter, the arc RQ, which is this arc here, the arc RQ is a semicircle. We're going to use the word instead of, I was just checking to make sure, is a semicircle. That means the measure of RQ is 180 degrees, right? We know that. RQ is 180 degrees. Since, and okay, here's what I'm going to do. Because we already know something about this, this angle C that we can use to conclude what we need to, right? So if the arc RQ is 180 degrees and C is an inscribed angle attached to that arc, then it has to be half that, right? So forgive me for this, but I'm going to scribble out this. This is a different way to prove this, and it's just kind of unnecessary because there's an easier way to do it. So I'm going to write what we're doing right here. Since angle C is an inscribed angle, inscribed angle on arc RQ, its measure must be 90 degrees. That's what we concluded. So we're going to keep going like this, we can conclude that angle C must be 90 degrees. There we go. That's super messy, I'm sorry. But this is a better way to prove what we want to prove here. And I'm not sure why I used the other. So to summarize what we just decided, right? Since RQ is a diameter, RQ goes through the center of the circle. I will use a pointer. Since RQ is through the center of the circle, then the arc RQ has to be 180 degrees. And because this angle is an inscribed angle on that arc, then that means that it has to be half of the measure of this arc, which makes this 90 degrees. So now we can use that fact whenever we want to, because we've proven it. So we can use the fact that the angle C is 90 degrees if that one side of the triangle goes through the center of the circle, which makes it a right triangle, sorry. Yeah. Okay, so now we have a picture here of a triangle with one of its sides going through the center of the circle. We just concluded that because of that, this is a 90-degree angle. There it is. And now we have 2 angles out of 3 in a triangle, and we can use that to find out what, I'll use B, find out what that other angle is in the triangle. So we just need to take it away from 180 because our total interior angle sum of a triangle is 180. So I'm just taking both of those away. And that gives me 142. So that arc is angle is 142. Nice, good deal. Okay, similar thing over here. We have 2 triangles that are butted up against each other, and both of them are sharing this side that goes through the center of the circle, which means this angle and this angle are both 90 degrees. So I'll write that in there. This is 90, that's 90, because we've just proven that. And so it's so similar to the other problem here that we can just we have 180 degrees for both of those triangles, so I'm going to take away 90 and take away 48 to figure out what's left for angle B. And that gives us 42 degrees if we do that math. And then the second triangle is the same. We do 180, take away 90, take away 53, equals C. Yes, okay. And C must be 37 because of that math that we just did in our heads. 37 degrees, 42 degrees. So I'm sorry about the messy part here, but all we're using is the fact that if a triangle has one of its sides going through the center of the circle, then the opposite angle would be 90 degrees. So it's a right triangle, and we use that fact twice in these problems. And that's all I have for you today.